Hello, everyone. So today we are presenting our project called SeBaR, which stands for Semantic Behavioral Alignment for Recommendation. So the basic idea of our work is that in recommendation systems, we usually either look at what users do, like their interaction history, or we look at what items mean, like their metadata or descriptions. But these two are usually treated separately. In our project, we try to combine both of these in a unified way so that the model can understand both user behavior and item meaning at the same time. So the problem we are trying to solve is this gap between the behavioral and semantic recommendation models. Behavioral models are good at capturing patterns like users who like this and like that, but they don't really understand why. On the other hand, semantic models understand content, but they don't always match real user preferences. Also, in our setup, the ratings are binarized. So we are not predicting exact ratings. Instead, we are solving a ranking problem where we recommend top items to users. Because of that, we evaluate using NDCG and HitRate, which focus on how well the ranking is done. Now I'll hand it over to Ishika to explain how we approach this.
Yeah, so this slide basically shows the difference between the two approaches. On the behavioral side, we use interaction history, which is good for capturing patterns between users and items. But the problem is that it doesn't work well when the data is sparse or when new users or items come in. On the semantic side, we use text or metadata, which helps in understanding meaning and context. But just because two items are similar in meaning doesn't mean the user will actually like both. So both approaches have their strengths but also some clear limitations. That's why we need a combined approach. Moving on to the next slide. So here it is. This is our solution, which is SeBaR, where we combine both behavioral and semantic information in a structured way. The model has four main components. First, we learn embeddings from user interactions using a behavioral encoder. Then we learn embeddings from metadata using a semantic encoder. After that, we align these two representations using contrastive learning. And finally, we combine everything and predict whether a user will like an item or not. The key idea here is not just combining, but actually aligning the two views. Moving on to the next slide. So here we show both encoders in more detail. On the behavioral side, the input is a binarized rating matrix, and we use models like light CGN or BPR to learn embeddings. On the semantic side, we take user and item metadata like profile text or genres and pass it through a language model to get embeddings. So now we have two different representations for the same users and items, one based on behavior and one based on meaning. Now I will pass it to Piyush to explain how we connect these two.
So yeah, this is actually the main idea of our model. Till now, we have two separate embedding for the same user and item, one for the behavioral part and one from the metadata. So what we do here is we try to bring them closer. If both the embeddings belong to the same user or the same item, we treat them as similar and pull them closer. If they belong to different users, we push them apart. So basically, we are teaching the model that these two views should agree with each other, and this helps in making the representation more meaningful overall. So yeah, moving on, once that alignment is done, the rest is pretty straightforward. We take all the embeddings, behavioral and semantics from both the users and item, then combine them, and then we pass them through a simple neural network. The model gives a score which tells us how likely it is that the user will like the item. And based on that, we rank these items, which can be clearly seen here. And then finally, this is just a summary of our whole pipeline. We start with the two types of inputs, interaction data and metadata, and then we process them separately using two encoders, as you can see here. And then we align them in the middle, and finally we combine everything and generate the recommendation score. And these scores are what we use to compute NDGC and hit rate. So yeah, that's the complete flow of our model.
In this demo, we'll walk through our code implementation for the project. The main goal is to compare different recommendation approaches, a popularity baseline, behavioral only model, semantic only model, and our proposed approach. Now, over here, you can see the project structure. Now, the YAML1M folder contains the MovieLens 1 million dataset. The SRC folder contains all of our code files, the implementation, data loading, feature creation, models, evaluation, diagnostics, and EDA. The output folder stores all of the generated plots, tables, and the saved model files. And the main file, which is runproject.py, runs our project. Now, in runproject.py, we first load the MovieLens data, create output directories, and run EDA. Then we create a leave one out train test split where one positive item is held out for each user for evaluation. After that, we build both behavioral and semantic features. Then the script trains four models: popularity baseline, behavioral only model, semantic only, and finally the hybrid model. Each model is evaluated using ranking metrics, HitRate at 10, and NDCG. These metrics check whether the correct movie appears in the top 10 recommendations and how highly is it ranked. In features.py, we create two kinds of representations. Behavioral features are based on user item interaction patterns, while semantic features use information like movie genres, release year, user demographics, favorite genres, and recently liked movies. This allows the model to understand both what users do and what the movies mean. Um, this file contains the model logic. The popularity recommender ranks movies based on global popularity. The semantic behavioral recommender can run in three more modes: behavioral, semantic, or hybrid. In the hybrid mode, it combines both views and learns to score user item pairs for recommendation. Over here, you can see that the full project has run using this command. Now, after running, the script prints progress for loading data, creating features, training each model, evaluating them, and saving all plots and results table. Um, the dataset contains 6,040 users, 3,883 movies, and around 1 million ratings. The sparsity is around 95.7%, which means most users have rated only a small fraction of all movies. This makes recommendation challenging. Now, going on to the plots, we have plots like rating distribution, genre popularity, rating per user. These plots help us understand the distribution of ratings, popular genres, and user activity patterns. This file stores all of the final results for our code run. It has the values for hit rate and NDCG for all of our four models.
Here are the final results. As you can see, the popularity baseline gets a hit rate at 10 of around 0.5. The behavior only model improves this to around 0.706, whereas the semantic only model lowers the performance to around 0.4. But the semantic hybrid behavioral model performs the best with a hit rate of around 0.72 and the NDCG of around 0.437. This shows us that combining behavioral interaction patterns with semantic metadata gives the strongest recommendation performance. To conclude our project, we implement a complete recommendation pipeline from data processing, EDA, feature engineering, model training, and evaluation. The hybrid model gives us the best ranking performance, which is our idea of combining behavioral and semantic collaborative filtering. This is Group 9. Thank you.